Let's say we have a population A of individuals who are certainly unaffected by a certain disease. They are 100% free of disease. We know it because we previously verified it. Now let's put that population A to test, and see how individuals distribute themselves around a range of possible test results. Let's say that the test results are almost discrete, and that the distribution we get is normal standard distribution, so that we can visually recognize a bell pattern. Now, given the x-axis value -1, the corresponding y-axis value is called likelihood. The likelihood of -1 is the y-axis value, matched with the -1 value on the x-axis of the normal standardized distribution. The latter, being a probability density distribution. Population B, on the other hand, is made up of individuals invariably affected by the disease. So they're ill, no matter what. Population B has its own normal distribution around test results, and you can see it plotted on the right side. Apparently, the mean of this distribution is right-shifted, as compared to the A distribution, and its standard deviation is wider. That doesn't affect the total area under curve anyway, as it is invariably equal to 1, whichever the distribution shape. Let's choose a cut-off point on the x-axis, and say it is 1. The likelihood of the value 1 is the same upon the two curves. So, at cut-off 1, the individual being tested is equally likely to belong to population A or B. Let's say that a person being tested for the disease will turn positive if the test result is greater than 1. Given the variability of the likelihood across test results, we shall take a mean likelihood for the specified interval of possible results for both curves. Say, on average, in the specified interval ranging from 1 to 7, the likelihood of population A equals 0.024, while the likelihood of population B equals 0.120. The likelihood ratio will then be 5 to 1. So, for each 6 persons randomly chosen from population A and population B to be tested, we can expect 5 belonging to population B, and 1 belonging to population A. The same ratio can be obtained dividing the areas under curve of the two populations, in the interval ranging from 1 to 7. And as I mentioned before, for each of the two distribution curves, the area under curve is equal to 1, so those areas highlighted in blue and red are probability densities. Their ratio is equal to the likelihood ratio. That's because the mean likelihood is proportional to probability, in a specified range of test results. Now let's plot a confusion matrix. 75% of the total population B are positive. As a result, 25% are negative, falsely negative. 15% of the total population A are positive. As a result, 85% are negative, truly negative. Note, the persons being tested are equally likely to come from population A or B before test. If positive, their likelihood turns into 5 to 1. Another way to look at likelihood ratio for a positive test result is to consider that 75% identifies the percentage of true positive in the population B. We can address it as the sensitivity of the test. On the other hand, 85% identifies the percentage of true negative in the population A, in other words the specificity of the test. So, the likelihood ratio for a positive test result equals sensitivity divided by 1 minus specificity. I didn't mention before that we were considering the prevalence of the disease in the total population A plus B to be 50%. What if the prevalence wasn't 50%? Let's say it is now 20%. We can adjust the values in the confusion matrix on the basis of sensitivity and specificity. So, in this case, 75% of 20% is 15%, and 85% of 80% is 68%. Now we are starting with a likelihood ratio of 1 to 4. So, if we randomly pick up 5 persons from the two populations, we can assume that 1 comes from population B, and 4 come from population A. So, before test is applied, the odds of disease are 1/4. Likelihood ratio is what we need to calculate the new odds ratio for the disease in case of a positive test. Initial odds times likelihood ratio equals a final odd of 504. This means that 56% of people who tested positive come from population B, and 44% come from population A. In other words, the post-test prevalence of disease will be 56% instead of 20%, in case of a positive result. So, if pre-test probability of disease is 20%, post-test probability will be 56% in case of a positive result. This could have been accomplished simply by dividing the percentage of true positives by the total positives in the confusion matrix, Bayes' theorem.